today our topic is artificial intelligence, and we'll take a look at deep learning, what it is exactly. So one of the fascinating challenges we have today in the industry, in the tech industry, is to keep up with the trends, but also to understand how the trends in the market could affect the way we work, we live, and communicate. And though there's a certain, there's a profound uncertainty of whether these emerging trends will be successful or not, but the challenge is for us to understand what these trends are and whether they will apply to us and how do we work together in the community, to move forward these technology trends. For us at Genesys, so later we'll have a talk with Merijn, our CMO, on why we are doing these talks, why it's important to us as a company, but also how do we work together with people in the Bay Area to advance those trends. And today's topic is about deep learning. So we have Abhishek and Sujit. So, so thank you guys for doing this for us today. So let me just start with a brief introduction. So Sujit works at Elsevier Labs, which is a research and development group that builds intelligent systems around research content. Yeah. So he's currently focused on applications of deep learning to image search and classification. And then we have Abhishek. So Abhishek is the organizer of Deep Learning Enthusiast Meetup group in the Bay Area, is that correct? He's also a software engineer at Salesforce. So he received his master's degree in computer science, focusing on artificial intelligence, and he was the recipient of an AI award in 2014. And then we have our CMO, Merijn. So Merijn leads the product group and our marketing group, but Merijn is not your typical average CMO. So very often you'll find him in his office playing with his Barbie with an excuse that he's researching AI. But learn more about
being recorded, by the way, so...
Yeah. So we'll learn more about his Barbie later when we have a discussion with him. But to start with, I'll pass it on to Abhishek. You'll be starting. Yeah, so we'll just switch this.
Am I audible? Am I audible?
Yeah, yes.
Thanks. Thanks, Candace, for the nice introduction. Welcome, everyone. So, today we'll give an overview about artificial intelligence, machine learning, and how deep learning is evolving, and what is the current trend going on in this. To start with artificial intelligence, we have been doing a lot of work on this area for a long time, and the definition of artificial intelligence kept evolving based on what we were doing, and there's not really a standard definition for AI. It's basically automation or writing intelligent machines or programs, and there are a lot of branches of AI. For example, knowledge representation, robotics, machine learning is one of them. And I like the most simplest definition of AI, which is it is the capability of a machine to imitate intelligent human behavior. So we are imparting intelligence to the systems that we are building. And mostly the reason is, as a human being, it's kind of tedious to do a lot of things. And automating a lot of tasks for us makes it easier to progress or to evolve technology. Some of the examples of artificial intelligence are like movie recommendations or the video recommendations on YouTube. When you make a credit card purchase, your company keeps a track of what the purchase is about, and based on your previous history, they kind of figure it out if it could be a fraud or anomaly in your purchase history. So you get those alerts that they saw a recent purchase of this, is this right, and all that. Then we have smart home devices which have come up recently, and Best example on Facebook is like when you upload a picture, it kind of detects some of your friends and it asks you if you would like to tag your friend or not. That's basically face detection going on in the background, and that's how you're getting the recommendation to tag your friends. And then video games are, there are a lot of multiplayer games which are extensively using AI. For example, people who are playing in one country, they communicate to people who are in another country in a different language, and there is a machine translation component which is going on with the background, helps them communicate. And even the iPhone, or there are virtual personal assistants which are which companies have started with coming out with. And this is just an example of when you log into Amazon and it gives you recommendations that based on your history of purchases or based on your viewing history of products, these are the items recommended for you. This just shows the trend or the relationship between AI, ML and deep learning. It's just the search terms that have for the past 5 years. It's available on Google Trends. And we can see that how deep learning is evolving very quickly. So this represents machine learning and this here is the AI. They are kind of close to each other, but deep learning has like doubled up in the couple of years, past couple of years. So what is? Let's look at the relationship between these three. The machine learning is basically a subset of AI. It's one branch of AI. And there are other parts of AI such as I mentioned earlier, robotics or the knowledge representation or symbolic logic. All these are AI, but there's also a huge overlap between ML and other branches of AI. And deep learning is another subset, is a subset of machine learning, which is an evolution of existing machine learning algorithms. Just that it's a bit more complex, but it's a bit more focused more towards the data. And Sujit and I will make an attempt to give an overview of those things today. Let's look at machine learning. It's basically writing the programs or the algorithms which try to learn based on the data or examples that you are giving them. The data that you're giving them is called training data set, and your algorithms your program learn from that. And how do we learn is what I'll be talking about in the next few slides. The goal of machine learning is to come up or learn a function based on the data that you have given and come up with the correct predictions for the new input data that you will be presenting to your model learn. So we basically here choose a function initially, which could be a logistic regression or support vector machine or anything else like random forest. And then our goal is to optimize the parameters such that the loss is minimal. Loss here represents the difference between the predicted value and the actual value, and it's represented by that term here. There are other things like regularization or generalization, which I won't be covering for today, but you are welcome to ask me at the end of the talk, or you are welcome to look it up. I'll start with an example for character recognition. Let's try to run an algorithm, or I ran an algorithm on this data set, which is a collection of clips from publicly available fonts. So this data set is available in form of images, and what I tried to do was recognize the character in those images. This is just a subset of the data set that I use. And then I ran the algorithm or the function that I chose on this data set, and I came up with a model, and then I tested on the test data set, and the accuracy that I achieved was around 85%. And this code here is basically there is a library called scikit-learn. It's Python-based library. I use that to write the program here, and it's kind of plug and play. You just you call the API that you want to use, and you train your model on that, and it gives you a model, and then you can test the model on your data set. So first let's try to understand what am I saying when I say training data set or the test data set. So when you want to train an algorithm or a machine learning algorithm, you basically need a data on which your algorithm will try to run. And we initially split that data into two parts. One part is called the training data set, which we use to train our algorithm. And the other part is called the test data set, which you would use to evaluate the performance of your algorithm that you have learned. So it is important that the algorithm doesn't encounter the test data, because if while learning, otherwise it will already know what is going to be the output. So you will not be able to perform, you will not be able to evaluate your model properly. So that's why we have a test data and a training data set separate. And during the training phase, we basically extract the data. We extract the features from the data. So feature is basically something that your algorithm will understand. For example, in my case, I use images, and the algorithm or the scikit library, the algorithm that I was using doesn't support the images. So I had to extract the features from those images and convert them into a format that the algorithm would understand. And then I can learn, and then I could learn based on the example. So I extracted, there is a feature called pickle. It's a module in Python. I converted these images into pickles and pickle format basically, and this is how the images looked after I converted them into pickle. And I am displaying the images using a plotting library called pyplot in Python. So this was the original image, and this is how it looks after the conversion. And this is again this random subset of images which I converted. And after converting them, I normalized the data. I had to make sure that since the images are from different fonts, and they will have certain, they might be different values, and they may not be related to each other. So I had to make sure that all the values, all the features that I'm using to train my algorithm are balanced or normalized. So I did some data normalization on that, also called data curation. And then when I call the API for logistic regression to generate the model, it learns the weights of all the parameters based on the examples that I provided. Weights basically represent the importance of a certain property. For example, if you want to buy a house, and or let's say you want to predict the value of a house in 2020, then to train your model, you will give the historical data, and some of the features could be number of bathrooms, or the area of the house, or the price of the house. These could be the features or the properties that represent the objects that you are using in your data set. And based on those properties, our algorithm would learn and will make a prediction that how the house price would be and what the house price would be in 2020. So similarly, I had some parameters which my algorithm would learn, and since scikit-learn is, they are doing this internally. We don't have to mention these properties specifically unless we want to. And based on those weights and parameters, it finally gives me a model which helps me in predicting those characters. I'll just give a quick overview of the function that I chose. It's called logistic regression. It's nothing but this equation, and this W transpose here represents the weights, X represents the features, and it's there. The equation is in a vector form. And B represents a bias term, which is for visualization, or we add some bias to encounter the data that we haven't seen, our algorithm doesn't see to begin with. And Y is the predicted value. So the goal of learning the model is to minimize the loss, which I mentioned earlier, and loss is basically the difference in the predicted value and the actual value of your data set. And so to minimize the loss, let's say this is what our loss looks like, and we are somewhere here at the top when we initially start our model learning. And our goal is to reach the minimum in the graph. So we start from a random value because since our model has learned nothing, since we're just starting, our weights are not initialized properly, so we are at the our loss is very high. We have to minimize the loss. So it's an iterative process, and with every example you take, our algorithm try to compare with the model learned so far, uses the weights learned so far, and then compares with the actual value, and based on that it makes the changes or updates the weight in the model. And with every step, the model moves towards the minima slowly. And once we reach the minima, we'll have no changes in the weight. So our model tries to update the weight every time it encounters an example during the training phase. And if it sees a huge change in the weight, it updates the weight and it goes to the next step. And once we see no changes in the weight, or the delta and W is 0, that's where you have the final model in your hand. After we have learned the model, it's important to evaluate the performance of your model that you have learned. You want to know that if it is going to make correct predictions or not, would it work with the real data that it has not yet seen. So that's where test data comes into picture. We use a test data set to evaluate the performance, and yeah. So this is what I got. These values are the predicted value which the algorithm predicted, and this is the actual image. It's not 100% accurate. It's very difficult to achieve 100% accuracy, but you can tune the parameters or your model to improve your accuracy. Mine was just basic direct call. And also sometimes the number of examples that you are giving to your algorithm, they also affect the accuracy. So if you have less examples, it is more likely that your model will not perform well because it has seen only a certain number of examples. If you add more data, then it gives good learning experience to your model. It's just like it works with us. Like if I study more, then I become an expert on that topic. And if I study very less, I will not know everything. But as we can see here, this image is some character which I don't know, but it thought that it is G. And same here, it thought that this image is E, but I'm not sure if this is F or something else. So the accuracy that I got is 85%. And I just want to quickly mention about the ground truth values. So when we give a data set, every image had a label, which was the actual value of that image. Otherwise, I would not be able to find out the loss because I need something to compare with. I need something to compare my prediction with the actual value. And those ground truth in machine learning are generally given by domain experts or the person who is running who's building the model. In this case, that someone had already prepared the data set, so I just used that. But in some cases, it may not be possible to label the data on a large scale. So there is some companies hire other people to do that for them, and it may not be always 100% accurate. So that also affects the accuracy of our model. So if your ground truth is not accurate, then it is possible that your algorithm may be right. You might have tuned the best way you could have done in your algorithm, but since your ground truth labels that your algorithm is based on, they are not correct, you will have a bad performance. Your model will not perform good. So it is important to have the labels accurate. Another example, I have another example here is to classify whether an email is a spam or not. I would like to ask you to try it out on your own because it's an implement. I implemented an algorithm called knife-based classifier, and this is where my implementation is available. You can just download it and provide the data set. It will run, and you can check out the accuracy. It will be a good exercise if you would like to know more on this. I'll just give a quick summary on the general approach that we use. So we have the training data, and we extract the features from the training data, and then we pass them through our ML model, and it's an iterative process where our model is prepared based on the weights that we are learning, based on the examples that we encounter. And during the testing phase, we just run the model that we learned in the previous phase on the prediction, and then get the predictions. And there are a lot of other things like the type of machine learning can be further classified into supervised machine learning or unsupervised. And I'm not covering them right here today, maybe another time. But yeah, so I'll just give a quick gist of those. Supervised machine learning is when you have the labels for your data. Unsupervised is when you want to, when you do not have the labels. For example, you want to cluster, you have a random data set and you want to find the groups in those data sets. So that's unsupervised machine learning. K-means is an example of unsupervised machine learning algorithm. So it helps you find the clusters in a given data set. For example, you have like different people and you want to, based on their profession, you want to group them. So K-means clustering can be used to cluster the people into different groups or some other properties. That's just an example. Classification is the process of classifying things. For example, that's what we did here. We were trying to classify if image belongs to one of the categories in the alphabets. So that's the classification. Yeah. So this brings to the need. So as we saw earlier, that our ground truth or the label that we provide to our algorithm decides the fate of our model. Lot of ways, there are a lot of times when this goes wrong and it affects the performance of the model, and that's where the need of deep learning arises. So deep learning kind of automates the process of feature extraction. It learns, it tries to come up with its own features, and with the help of deep learning we can even learn more complex features which may not be possible humanly. And it does computations in a complex way. If you have like more layers, which Sujit will be explaining in a few minutes, then it's may not be possible to apprehend those, what are the exact features in a particular layer. And deep learning has certain small building blocks which we can combine and make complex models. And so in my example here, I was just trying to predict one of the categories out of 26 alphabets. But in some cases, there might be complex predictions involved, and so deep learning is really good at that. These are called non-linear classification. So deep learning is really good at that. But there are certain cons with deep learning. One of them is it has a tendency to overfit. Overfitting is when you add more and more properties or more and more features to your learning model, your learning model kind of sticks to the data. It becomes very close to your data. So it will perform good on the examples which are related to your training data, but it performs very bad for the examples which are not related to your training data. You don't have a slide. I wish I had put a graph here explaining the difference, but I apologize for that. So it's basically your learning model is only kind of confined to your training data, and anything which is outside the training data, it will make a bad prediction. So that is what is overfitting is, and deep learning has a tendency for overfitting. But there are ways which we can prevent that. And another con is we need a lot of data, because deep learning is trying to come up with its own features, so it needs a lot of data. And historically, neural networks or the deep learning, which are also known as which are the components of deep learning, they were like people were working in early 90s, but they were not a huge success. And the main reason for that was there was not a lot of data available at that point of time. And nowadays we have a lot of data, so that's why I feel that this is what the main reason is why deep learning is evolving so much and it's doing so nice a lot of things. And then it's very computationally expensive. So neural networks has layers and they make some, they do some computations internally, which takes a lot of time, and sometimes your model can run for 3 to 4 days on the data set. Now Sujit will give you an overview of data.
So, well, this is kind of an example of a classification problem. There can be other kinds of other kinds of machine learning problems as well. But if you think about back to what Abhishek said about house prices, so you could think of the X matrix. Okay, so going back a little. Typically, you would want to decompose your problem into a matrix of features and vector operations, right? X and Y. So what are the features? I mean, for instance, if you look at house prices, maybe the number of rooms, maybe the area, maybe the school district, right? So those kind of things would be the features that determine the price. The Y here would be maybe bands of prices, under 500,000 or 500,000 to a million, right? So that's what. And so the idea is that you try to discover a function f, which is the one, which converts. Where is this? Okay, it takes x and converts it to y, right? Obviously, the conversion is not perfect. It's not analytical. It's a numerical method. So now, because the conversion is not perfect, what you get is maybe something like y hat, which is different from y, right? Which brings us to a loss function. The loss function is the difference between the label and the prediction, right? What you predicted, the model predicted, and what the label was. This is one particular kind of loss function. This is the squared loss, root mean square, I think it's called. Yeah. So the idea and the whole point of building this model is to minimize the loss function, right? So let's go over. Now, if you were to think of, okay, so we looked at a X matrix, right? So imagine an X with just 2 features, right? And if you now draw a graph and you write the loss function, on the X value, you will have the loss, right? And a typical loss function looks something like this. It doesn't look nicely, nice concave, or it doesn't look like that. So, however, the approach that we are taking is that we are trying to do gradient descent. Now, gradient descent in case of a perfectly convex loss function is guaranteed to give you an optimal, right? And that's the best possible thing that you can get. However, in this case, it can give you the best local output, which may or may not be good, right? However, if you there has been some research saying that if you go into high dimensional space, local optima are usually good enough, right? And so that's what you're like. That's good enough. So we'll start off with, this is mostly high school kind of algebra and calculus. It's not very hard. So if you think about solving a linear equation, right, a line is y equals mx plus b. Now, if you think now about, let's say, instead of one equation, you have, say, hundreds of equations. So we go into simultaneous equations, which is basically a vector y with a vector x with a weight matrix y and offset, right? It's just a vector. So you can basically formulate this whole thing as a vector, right? So that's basically all you need to go and what you just kind of relearn this. Now, if you remember, so a linear system of equation is capable of solving a linear problem, right? So if you have a perfectly straight line, real life isn't that. So what early neural networks, they came up with the idea of a perceptron. So what they did was they basically imagine a system of many such functions which takes the inputs, combines them in some way, applies this kind of step function to it, and says either 0 or 1, right? And a network of many of these perceptrons would be your model, right? And so the idea is that, so this is kind of modeled on the brain. little axons all connected together to produce intelligent stuff, right? And so this was our perceptron, which brings us to the sigmoid neurons, right? So instead of a step function, we replace it with something like this. The equation for this is this, and what we do is we apply the same. If you remember the equation for the linear equation, right? You apply the nonlinearity on that, and what happens here is that instead of a discontinuous function, this is now a continuous function. And this function is differentiable, which is a big deal. It's a big deal because you suddenly now you're able to calculate the loss as a gradient, right? So that's kind of where and of course, I mean, the sigmoid was one of the first activation or nonlinearities to be used. However, nowadays you use things like values, which are much computationally much simpler. Use tanh, which is which operates similar to sigmoid, but operates from -1 to +1. This operates from 0 to 1. Okay. I'm going to go more in the programming aspect of deep learning. So obviously, if you were trying to do the same thing, you would look at toolkits. There is this nice link here. This guy actually lists out not only 9, he lists out close to 13 deep learning toolkits and that he likes, right? And there's more coming up every day. And just yesterday, I heard of something called TensorFlow Slim, which is kind of like Keras here. However, these are the 3 I know. This is the 3 I use. So this is my endorsement, but take it for what it's worth. So, like I mentioned, so if you think of actually what Abhishek mentioned, that neural networks is kind of a different kind of hammer, if you will. I mean, it's machine learning is one kind, and the idea is that you can compose little blocks and you can compose it into large systems. Right? And the idea is that you want to handle nonlinear kind of data. So if you look at this data, so I'm going to show you a little demo first. So if you look at this data, you can actually segment this linearly, right? Almost linearly. Not so easy with this, and definitely not possible with this, right? So this is on GitHub. So if you guys want to go and look later on, it's totally fine. So essentially, what I'm going to do is, I got this. These are synthetic data sets, and basically, I read this data. Can you work? So I essentially, get this first, and then I basically create my data, and I want to show you the model that I used here, right? So this is my model. It's a fully connected network, and it has just one hidden layer, right? The hidden layer of 2 units, and these 2 units, because it's almost a linear problem, this is like a really, really simple model, right? And this is all Keras code, and I want to show you how easy it is to actually write code with Keras. So if you could go all the way up until we reach there. So if you look at at the end of this, it came out with a 92.5% accuracy, and it doesn't take much time, and it's really simple code, and this is what it looks like, right? This is what it looks like. If you notice that there is a linear line, your original line was not linear, not perfectly linear, so it is approximated it, but it has made a reasonably good 92% approximation. Okay? So if you go to the next one, this is slightly more, obviously harder. The model here is also a little larger than before, right? Now it's like 4 times the code. It has 2 hidden layers, and there is a nonlinearity at the end of each, one ReLU and one softmax. So if you go up, this, if you look, this is also giving you, almost a linear kind of calculation, but its accuracy is much lower. If you increase the size of the hidden units, right? So instead of 2 and I actually now I have one more layer here, right? So 50, 100, and 2. So I get a slightly better result, but it's still very linear. So this goes on like this, and if you keep going all the way up to the last picture. So, this one is actually much larger than, we're trying to solve a harder problem. And, if you, and you'll notice at the last picture, so if you notice here, right, so the separation has become kind of nonlinear. It's getting not linear anymore, right? So, and towards the last, as a much more complex model, you'll see that, it's really going all the way in like this. So it's changing, right? So the more hidden units you apply and the deeper your net is, the more nonlinear it is. Right? That's the kind of point I was trying to make. Okay. We can go on. Okay. So this was it. So we talked, Abhishek also talked about building blocks, and these are three kind of basic building blocks, right? There are more, there are much more complex ones, but if you were to start with neural networks, you would kind of need to know that this is a fully connected network, convolutional network, and recurrent network. These are aimed at different problem spaces. This is obviously the fully connected is the first one to ever become popular in deep learning, even in the 1970s neural networks era. Usually, it has been applied to almost everything because it was just there, the first, right? Convolutional neural networks, it exploits the geometry of the input. So if you look at an image has an x and y, right? So unlike if you were to flatten the image, so the first column, and the first column, second row are not neighboring. They are out here, right, if you flatten it. However, if you make it into an x, the xy space, now they're right next to each other. So the convolutional neural network, it exploits the geometry, right? It is able to do that, and obviously, the biggest application is to computer vision and video, and also to some extent to natural language processing, because natural language is one-dimensional, right? Again, you have, there is a concept of neighboringness, right? So if you have a one-dimensional convolution, you could use it for natural language processing. Recurrent neural networks, it basically exploits the temporal nature, which is again natural language, audio, speech, right? And it has been applied to everything, but mainly to natural language processing, machine translation, image caption, etc. All right. So a little bit deeper into each of these guys. Again, fully connected network, inspired by biology. The nice thing here is that every node, this layer will share the same weight, and this layer share the same weight. When you talked about the W matrix, right? The W matrix is common for this and this. They don't share weights across. And the idea is that the inputs flow forward using something like this. So you take the layers. You take, sorry, actually I should use this. You take the inputs x here, and you pass them through this nonlinearity, and what you get here is this value, right? And the errors that you get, so this creates some kind of predictions here, and you know the limits. So you're able to now calculate the error, and you take this error at each layer, and you pass it back, right? And update the weights as they go back. And so, you keep going back and forth, and ultimately it all flattens out. It doesn't move anymore, and that's when you stop. This is a demo. I'm going to go really quickly through this because it's once you've seen one kind of network code, you've kind of seen them all. It's just more. If you could. Thank you. Okay, so this, you might be wondering why we keep doing handwriting recognition. It's kind of the hello world of deep learning. So everyone does it, so that's their nature. So essentially, I'm downloading data, and here's my model, right? So again, a little bit more complex than what we saw before. We have an input layer, we have two hidden layers, and we have an output layer, right? The input layer is of size, so it's 28 by 28 pictures. So you flatten it out, it becomes 784 features long, right? And so the input shape is 784, and the output shape is the number of classes. In our case, we have 10 digits, so the number of classes is 10. Right? And so if you do this, and you run this whole thing, and then you'll see if you. So this is how the loss function behaves, right? So as you train the model, initially the loss is very high, and then it starts flattening out, right? And then it becomes like, it doesn't get better, much better than this. So once you have trained the model, you take the trained model, and I took some random images, and then I tried to predict it with my model. So here's a tree, and here's a tree, and so forth, right? I mean, it doesn't do it all correctly, but most of it does correct. And I think I don't remember how much it was. I think it was about 92 or so accuracy. So this is fully connected, and the convolutional neural networks looks like really complicated. It's inspired by the visual cortex, the way we see. When we look at a particular thing, our cortex basically breaks it up into little pieces. And this is exactly how this happens here. So too much. So what happens here is that you take each little, you break this image up into little pieces, right? And then each little piece is run through its own convolutional net. And however, what happens is that all these convolutional nets share the same weights, right? So they actually, talk to each other and kind of create the weights together. And what you do here is you alternately convolute, and then you, it's called subsample, or in programming speak, it's max pooling or average pooling, whatever you want to call it. And at the end of it, once you have, so the idea is that you take these little pieces. At this point, this is like a few pixels wide, right? So maybe it's a line, vertical, horizontal, whatever, right? And as you go further down this convolution and pooling, it starts combining these things together and creating features. So if you were to send in a robot here, right, for this picture of a robot, towards the end you would actually see little pieces of the robot. And those are the higher order features that we are looking for. And that's what is now fed into a fully connected network. And this does the classification for you and says, okay, this is a robot or whatever. Right? And so little bit of convolution. I'm not sure if it's really interesting, but it's it is. I think it is. So what it does is the convolution operator. It applies this matrix on each element of the input image. So imagine that this is the input image, and this is your convolutional kernel. So essentially, what it does is it puts this image around this guy here, and this is all, at this point, these are all zeros, right? Because it's on the corner. So if you multiply each element by this, you end up with minus 255. And you could actually do it with all of them, and you'll see it comes out to this. Max pooling is much easier. This is a 2 by 2 max pooling. So it says, okay, find the maximum of this region, this region, this region, and this region. And we come up with this. So what you are actually seeing is that you are taking pieces of the image, and you're condensing it into smaller and smaller pieces. And so essentially what you're doing is getting higher order features, and then finally you're sending it to the fully connected network. Okay. So this is another demo. It's largely similar. I'm going to just show you really quick how the how the model is organized, but that's about it. This does work much better than the previous one. It gives you a higher accuracy. Here. So this is also, again, you create a sequential model, but here you have convolutional layers, right? And you say, okay, I want a convolution, a nonlinearity, followed by a pool, right? Again, convolution, nonlinearity, followed by a pool. And finally, you just say, okay, I put it into a fully connected there, and then it predicts one of 10 numbers. That's it. And the rest of it is very similar, so I'm not going to go there. All right. And finally, this is recurrent neural networks. It's the most complicated looking, but it's actually not that complicated. The biological inspiration here is memory. So imagine, I was saying something, and what I'm saying now is dependent upon what I said a few minutes ago. Right? There is context. So therefore, it's the idea is that we keep context. In case of the other two, there is no concept. There is no concept of memory. Right? Everything is independent. So here, if you think about this, okay, here, so this is what a typical recurrent network would look like. So the output of, so input comes in, the part of the output goes back and feeds into itself. And if you unroll it across time steps, so if you say this is a time step 0, 1, 2, 3, right? Input at time step 0 produces an output at time step 0, but it also sends a hidden amount of this output to the next layer, right? And the input of time step 1 is now combined with the output of time step 0 and creates the output of time step 1, right? So essentially this equation. And as before, you apply the nonlinearity. I'm putting a sigma here, it doesn't actually mean sigma. Sigmoid could be other nonlinearities as well. Okay. And the thing about the weights here is that it's shared across all these weights, right? It's like one single weight matrix that's shared across all these weights. Okay, so the obvious problem here is that because you're actually sharing your, you're taking this input and you're multiplying it with this input, right? And again, you're taking this input, multiplying this input. If your input happens to be less than 1, it keeps multiplying with itself and becomes very, very small, right? And on the other hand, if it's more than 1, it becomes very, very large, right? So these are called, exploding gradient problem, vanishing gradient problem. Exploding gradient problem, you can clip. You can say, okay, if it goes beyond a certain range, just chop it off. That works, strangely. But the vanishing gradient problem will actually, cause your network to not move at all. It will just stop it. So to look at that, so to kind of combat that, people came up with the LSTM. It's called a long short-term memory. Essentially, it's what it does is it has a forget gate built into here, right? So it, as this thing comes in, it has another gate which will bring it, very large inputs will go down and very low matrices will go up, right? Weights will go up. And so that is computationally very intensive, but it solves the vanishing gradient problem, and it's actually quite a popular network. The GRU, which is kind of an improvement over LSTM, it simplifies LSTM and results in better performance, but with no significant decrease in effectiveness, right? So it's kind of obviously there's trade-offs, but the trade-offs are not very apparent. If you want to, you probably should. This is like a really short introduction. You should probably go and read these things, and you'll see. There's much more to LSTMs than what I just said, but it's worth reading. So now I have. So we're talking about composability, right? So recurrent neural networks can actually be composed in many, many different ways, and depending on the problem, you can actually compose them. So if you look here, this is a many-to-many. I have a demo of the many-to-many, and what happens is that for every time step, at every time step there is an input and there is a corresponding output, right? Typically, you would use this for generative kind of problems where you want to say predict, right? So given say the last 5 inputs for a stock market, predict what the next day's closing price will be, right? So that kind of. The many-to-many is more very popular in machine translation. So what you do here is you send in English words, for instance, and once you say okay stop, it will start emitting French words. That's one example. One-to-many could be like you input an image, a picture with all the pixels, and it will output a caption, right? So you could train it to do that. A many-to-one, you could do like things like sentiment analysis. You feed in words for a sentence, and it outputs a sentiment. Right? I have 3 demos. I'm not sure if is there time.
Show one.
Okay. So let's go with let's see. I want number 2. Yeah. Number 2 is nicest. Also takes a long time. So this was a problem basically from the university course. course. They had their course was based on TensorFlow, but I wrote in Keras. Essentially, it's kind of a machine translation problem, but I was not really doing the translation. What happens is, if you can bring it down, the problem definition here. So essentially, what I'm doing is I'm taking inputs as forward sequences, right? And then I'm outputting reversed words. So THE, quit, brown, false, right? So that's what I'm doing. And I'm doing it at a character level, which makes it, at a word level, this is the trivial problem, right? Because you're saying, okay, I have a matrix, or I have a lookup of the, and that points to 0, and ETH is also pointing to 0. So it's transforming 0 to 0, so it's a trivial problem. However, if you do it at a character level, saying that, okay, taking this, vector of characters and producing this vector, it's a harder problem, and it kind of exercises the issue, this setup. If you could go up a bit. Okay. So here I'm just preparing my data, so I use Alison Wonderland, the text, and I use the words in there, and I'm creating my input data. And here is my lookup tables. I find that there is my entire vocabulary is like 42 characters long, 36 characters long here. And so then I vectorize it, and then here is my model. Again, if you look, this is an incredibly complicated model. However, code-wise, it's just a few lines of code, right? So what this does is this is an encoder, right? It takes your 4 words in, the characters, about 42 characters or so, in. Then it runs it through its own, this whole LSTM, and then it takes this output and it stores it in the output, and then it repeats this into the inputs for the decoder layer, right? And finally, it takes all of that, and for each output of the decoder layer, it creates, it gives you a 42-way classification. So identify the character. Okay? So I'll show you what, it's utter garbage if you look at the first iteration. A little bit more. Here. So if you think about, I took random inputs here, and I say, okay, this is my output, right? And if you look here, it says think nothing of tumbling. I expect to see this, but this is what I get, right? It's total garbage, right? However, if you keep going down, and after about 50 iterations, 50 epochs of training, you'll see it actually, it seems to be much better here. So if you look at this, up is the other, and this, it got it almost right. In fact, it got it exactly right. Okay? And I'm calculating cosine similarity. This is just, I think, it's an accuracy thing. Right? It should have been 1 versus 1. And ultimately, taken over all the averages, I'm getting 96.9 kind of accuracy. So this is what I have, and I think, yeah, can you go ahead? And so again, to reiterate, this is how things stand. Deep learning is a subset of machine learning, is a subset of artificial intelligence. Do you want to?
Sure. So, 40 minutes, 1 hour is not enough to talk about these topics in detail, and there are certainly a lot of things that you might want to learn in the future. So please feel free to check out these websites. And apart from, so these are, I would say, these are the textbooks which I referred when I was trying to learn about machine learning. And there is an online textbook for deep learning too, which I haven't put here, but you can find it. It's by Abhishek and Sujit. And there are a lot of MOOCs available on Coursera, Udacity, and they're also covered at our deep learning enthusiast meetup. We host it at Salesforce every Thursday from 6:30 to 8, so you are welcome to that too. And these are the references.
Alright, so thank you Abhishek and Sujit. So if you just stick around, later we'll open up for questions. But before we do that, we'll invite Merijn. up to you. So, Merijn, 2 years ago, you were on stage saying that artificial intelligence will become the singularity and it will affect everything and disrupt everything that we do. So, from a customer experience perspective, based on what we do at Genesys, how do you see artificial intelligence affect or disrupt what we do?
2 years ago. Oh, it was last year actually. So first of all, so I'm part of a little club called the Sharma. Yeah, it should be on. I'm part of a little club since I became CMO of the CMOs of the Bay Area. It's like 15 new CMOs that have been trying to figure out how to run an operation as a CMO. If I tell them in here that I listened to this and I understood part of it, I'm going to be kicked out. So I know this is recorded. I want to be really secretive about this one. So yeah, I think it was last year actually at GeForce I decided to start talking about some trends that I think are coming very quickly. This is where the Barbie came from as well. Is that around Thanksgiving last year, Mattel came out with a speaking Barbie, right? Now, speaking Barbie is not a big invention, but what they came out with was a Barbie that was based on artificial intelligence. At least a Barbie library of communication capabilities that allowed a child to speak to a so-called AI or AI-enabled toy. And I found that fascinating because, as far as I'm concerned, that meant that a new technology came into the living room, and as soon as new technologies come into the living room these days, it means it will have impact on what we do. 20 years ago, that was not the case. We were, in all our time, able to invent the IVR, and nobody gave a damn until we came out. And I'm not saying Genesys, but the vendors and, to a certain extent, enterprises. We came out with the IVR, and we sold it, and then customers started complaining about it. That's not the case anymore. So customers invented social, they invented mobile, and now they're starting to use AI, and they're starting to use all kinds of new technologies, making our legacy industry look silly. And that's why I started talking about it last year, to provoke my customers that were in that room at GeForce at the time, to start thinking about new ways of communicating and technology changes that are coming to them. And they're coming much faster than what we think. I don't know if any of you read Gartner news or hype cycles, for instance. They came out with their first hype cycle, I believe, in 2001. And at that moment, chat had the same position as artificial intelligence has today. Now, chat took about 15 years before it became a real mature means of communication. Video was already in that hype cycle as well. It was pretty close to chat, and that's still not mainstream. It's mainstream in peer-to-peer communication, but in the enterprise, it's certainly not. But I do think that when you look at all the technology available, that will happen really quickly, and it's exponentially quick today. I think that if we do not do anything as a company, Genesys, but especially as an enterprise and customer service with AI, or with IoT, or with machine learning, or with deep learning, preferably all of the above, then you're going to miss out. And if you miss out in these days' economies, you're going to be out of money very, very quickly. So for me, it is incredibly crucial. It will have a massive impact on everything.
Okay, good.
I guess we'll open it up for questions now. If you have questions for Merijn or Sujit or any questions?
Come on, guys.
Okay, there we go.
All right, I guess I would say this is a question for all three of you. So on a scale of 1 to 10, how much would you say you fear artificial intelligence, if at all?
Yeah, I can start that. I don't actually fear it. Well, for one thing, it's kind of selfish. It's not going to, malevolent AIs are not going to happen in my lifetime. So that's one. Secondly, I don't think, so I think as time goes on and we understand AI more, we would be able to program them. So, ultimately it's us who programs them. So I don't see, somebody who is stupid enough, I would say, to actually destroy the world that it is. Yeah, but I also have this similar opinion. I'm only passionate about AI. I don't fear AI, and I'm pretty sure that it's going to be used in a much more positive way. It is going to have a really positive impact on this society.
That's a 10 then for both of you. I'm a lawyer from origin, so I can't go with a 10. So I actually find it fascinating, and new technology comes out that gives a good laugh as well, which it does. I don't know, you probably saw Microsoft with their AI bot on Twitter, and within 24 hours, the whole field of society was assembled by that AI bot, and we had the new Hitler in artificial intelligence available, which is a good laugh. At the same time, it's also kind of scary what society is all about these days, right? What you can find if you let an AI environment just learn based on what we put in. So that's scary to a certain extent, because our society is not fantastically pink as far as I'm concerned. But in essence, if you, I'm not afraid of it at all. I think if you are able to use AI and see it as a complement to what our society brings, I actually do believe that 50 years from now, the human capital and the way the human capital will operate is in a much better place than it is today. So I'm embracing it, and I think it will add a fantastic complement to what we do. Do I think it will replace humans? In certain functions, certainly. And I hope it's mine, so I can play golf or whatever I have as a hobby 10 years from now. But I also do think that it will allow other opportunities to arise, and people will be much more entrepreneurial, supported by AI capabilities in the future. So I'm not afraid of it at all.
Thank you.
Any other questions? So I have a question for you guys. So the way we're looking at it is, for the algorithm to get to the nearest highest level of accuracy, you need a large data set. Is there any advancement in technology that could allow you to get more accurate with a smaller data set?
Yeah, there are possibilities. There is something called kernels. So that is one of the techniques that we kind of use to get more features from a smaller subset of data. So if you have a smaller subset of data, you can generate like not really fake, but more features using the functions called kernel, and they I could prove it. Like it can be proved mathematically that why those features are accurate, or how they help being on to the accurate. So there is a possibility, but it may not have as good performance as it would have with the larger data.
Can I add?
I think the current trends are for supervised, so basically that's the point of getting data. You need targets and labels, but I think most of the research is using unsupervised data that's available for us without labels and try to determine this. That's the current trend in academic research.
Some of it, you can intelligently use your knowledge of the domain to take unlabeled data and convert it into label. So, for instance, let's say you are taking medical risks. If you know the outcome, you know the outcome of this person, whether the person actually became sick or not. Right? That is kind of unlabeled, it's not supervised. Yet you can now separate the two kinds of records: people who are sick, people who are not sick. Right? And it's crude, but it's one way to do it. There is one other way where there is a project in Stanford called Deep Dive. They are looking at programmatically writing labeling functions. And once you have enough labeling functions, you use a very small training set to validate the, how good those labeling functions are. Essentially, what you're saying is that I have a bunch of weak labelers, right? And almost like crowdsourcing, right? And then you say, okay, how good are these guys? Right? And then based on that, you kind of generate your label data from that algorithm. So there are ways to do it, but it won't be as good as human label data, obviously.
There is an interesting project in this regard. It's by CMU, and they are trying to convert the textbooks which are not available in digital format through us. And they have this project called reCAPTCHA. And if you submit a form on the website, you will see some images, and it asks you to enter the characters that you see. So some of those images are from textbooks, and what they are doing is like they take from certain number of people, and most of them have answered the same number. same character, then they consider it as a nice character. So just an example of how we could label the ambiguity.
Okay, so another question for all of you. Is there any specific industry that you see AI being more successful, whether that's banking or retail? Is there any specific industry where you see it being more successful today?
Yeah, so I don't think there's a reason to expect that one industry will be more successful than the other. I think it's all about what kind of data do I have. And not so much AI actually, but more on the abilities to start predicting what outcomes will be like. And I don't think that will be very different from a bank to an insurance to a healthcare company. I think it's going to be more relevant to an environment where you have a large set of unpredictable outcomes today. You can jump high and low if you're a telco. Life is really there's an incredible amount of predictability already by simple business rules on how customers will interact and communicate with you. But if you're a bank and you sell a large portfolio of capabilities, or if you start diversifying, you buy other entities and elements like that, it becomes a really complex data set that they have no clue what to do with today. So they're not able to spot any patterns or trends or anomalies because they're all Excel games. That's how far they have developed. So I think that those environments will have a large possibility to differentiate themselves and really create an environment where everything becomes predictable. Because I think that and I'm pretty sure that you guys would not necessarily agree with that, but for me, the power of understanding or using that data is understanding and predictability. And for me, that would mean a massive change in our industry. Right? So today, nothing is based on predictability. Everything is based on hope. If I'm a contact center manager or customer service manager today, I hope my day will be good. And I think in the future, everything that they will do is going to be incredibly predictable. And I think that's a beautiful step. I don't think there's a vertical that will be incredibly different than other.
Yeah, you're very correct. So I feel that it's AI or machine learning has equal scope in all the industries. For example, if you see automobile industries, they are now using the data that they have to predict which parts of their machine might not perform good in future. So they are using that to detect failures in their systems or the machines that they have in the industries. And if you look at the healthcare side, the data of the patients is being used to predict what diseases they might have in future, or if that data, all the treatment that they were exposed to can be used to diagnose some disease in someone else, or can be used to treat somebody else. So you can find application of machine learning or artificial intelligence in almost all industries now. Since we have more data now and people have started to realize its importance, so everybody is trying to make use of that. And hopefully it will be.
Yeah. Also, if you've noticed, there is an ad for a car. It's Lexus. It calls itself a supercomputer. So I find it kind of strange that something that is really meant for locomotion now builds itself as a supercomputer. It's totally not related to its function. But it's kind of the sign of the times, all the data being used.
And it's happening everywhere, right? So if you take companies like Netflix, for instance, they don't care about content. They care about data that they derive, and they monetize the data. And the same is true with the supercomputing Lexus, or Tesla for that matter, or any moving vehicle that is in any way connected. Now we're getting into IoT as well, but in any way connected to something is becoming relevant because it generates data. I'm still utterly surprised, and we talked about it a little bit before, I'm utterly surprised that I walk around with a ton of credit cards. Whether I like that or not, but I have a couple of credit cards in my back pocket now. And they have no clue where I am. So these devices are not even enabled, they're not intelligent, they're not communicating, they don't tell my bank what I'm doing. They the entire service orientation of healthcare, of utilities, and they are ahead. And also insurance, for instance, there's no reason why an insurance company would not be able to give me a real-time, how do you say that, amounts of money that I need to make based on my driving behavior, based on my eating behavior, based on the fact that I started this morning at 6 o'clock at work and I'm still working. You could say you have to pay more because your health is under stress. So it's an easy thing to do, and they don't. So there's a beautiful world that's going to open up.
But to that point, there's also the issue of privacy, right? So would people be ready to share all this data and all this information?
So for me, that's really simple, right? And so I don't think we should look at our generation with all due respect for all the young people here, but when I look at my daughter, she can move forward by gamifying with her own data, that is her IP. And because of that, gets an additional Pokemon, or gets a cheaper phone, or better whatever sneaker it is. She will. So if it's in my benefit, so this is the opposite of loyalty programs, right? So I give you something and I get something back. In this scenario, it's me and my data is my IP. I own that blockchain-like capabilities. And with that data, I merchandise, I monetize myself. So if I want to pay a low premium on my car, I drive like a sissy. Not too much, because then I have to pay more. If I want to pay less health insurance, I eat healthy. And I allow my health insurer to understand that that is actually the case. So I gamify with my own way, my own desire, and if I want to get drunk one evening, I'll pay more for that day. So I have no issue at all with that, and I don't think the next generation will have a big issue with that either. As long as they feel that their IP is their IP, and it's not floating around, applicable to each and every one that wants to do something practical.
Several of you have mentioned healthcare as one of the areas, and I know a number of the people that I've been talking to have expressed concerns about HIPAA regulations, how they are really interfering with medical discoveries at this point, because there's a ton of data out there that can be addressed through machine learning, deep learning. It's not available. I mean, there's no signs on the horizon it's going to be available anytime soon. I wonder if you have any comments on that. Also, you mentioned the blockchain briefly in there. It does seem like the blockchain is potentially technology that could be used to create tiered sharing of data. And I thought maybe you could say some more about that.
Yeah, so I have Bitcoins, and I read that a little bit. So at heart, when you're a geek, you do that, right? So the fascinating element, though, of it, I think, is blockchain approach and technology. Because as far as I'm concerned, it would be the first step into me as an individual person owning my own data and IP that patent protected online, which makes HIPAA a completely different story. Right? So I think it's a good thing, by the way. As I said, I'm a lawyer from origin, and I graduated in international law, so the EU was a big part of me, so I'm very fond of everything that happens in the EU. The thing that they finally got rid of the English, for instance, I think is a good thing about it. But for instance, safe harbor is the same thing, right? So where do I store my customer data? I'm not allowed in Genesys to store any customer data from within the EU, or outside the EU. So that makes it not necessarily complex, and there's no real reason for it either. It's a government-invented system that no citizen in the European Union is actually very happy with. And I think the same will apply to HIPAA somewhere down the road. If it becomes very clear that because of that, we're not progressing with our healthcare possibilities at the speed that we could. And last year when we talked about the Barbies example, I did my presentation with a heart rate monitor on, right? So in real time you can see my heart rate. And that was for a certain reason, because until then I was like an ostrich. I would not do anything with data or go to doctors, etc., because I felt I was really healthy. And if I wasn't, I didn't want them to discover it. And then they discovered that I wasn't that healthy, and suddenly I used everything in my power to make sure that I can, whatever data piece, hand over to my cardiologist. And he said, I'm not allowed to do that. So I have to take my own blood pressure and write it down, and then go to my cardiologist and tell him this are the 10 last sessions I had, where I could just automatically sample that data, make it available for him at any given time. It's odd, as far as I'm concerned, and stopping progress. So I think that in time, when we have a blockchain-like capability, regulations like HIPAA, like EU safe harbor will change, and we'll adapt to that. That, by the way, the EU takes ages.
Yeah, I think this is also affecting the research that is going on. So I was researching with one of the professor at University of Illinois, and one of his students was working with one of the clinic, and just to access the data, he had to get a lot of approvals. So that kind of slowed down the research process. So, hopefully those barriers will
Let me ask you a question. Do you have a medical dossier on you right now? Like this file with all your allergies, with your blood type? Do you have that available right now? Can you access it?
It's something in Microsoft.
I still find it incredibly annoying that if I drop over now, right now, you will have a hard time finding my medical information. That should not be the case. Right? I'm heavily allergic to penicillin, so you should not give me penicillin. You have to access the medical database to find that information. Not that you're walking around penicillin and shoot it in my leg as soon as you find it. But it's odd that I cannot make the data available at any given time based on any rule or machine learning for that matter. So if I drop, I should have the possibility to alert everybody that this data is available and this is going on.
I think there are some people who are experimenting with cards that you can load that data
Yeah.
on and have carry with you all the time.
But it's an interesting, we're getting into it, but so we did some tests with that because we can use a smartphone quite well to predict what's actually happening. Right? So velocity of the fall or elements like that. In the US, we really step into a beautiful world of liability. So as soon as I offer that as a service from a Genesys perspective, let's say, I need to get it right 100% of the time. Or I have to price it at $100,000 a seat to make it affordable for me if something goes wrong and I have to pay the liability. But it's an interesting part of it. To a certain extent, HIPAA, healthcare in general, is stopping progress.
So I have a question. We've talked about AIs being used on behalf of businesses or services that could then offer things more intelligently or in more custom ways. What about the concept of individuals owning an AI or an agent that's autonomously acting on behalf of each person to optimize their interactions with enterprises, but for their benefit as opposed to feeding data into the enterprise from the person? Do you see any potential for AIs acting on behalf of each person and being loyal to the person rather than the business?
This is scary. I don't know if you saw the little video yesterday that came out of actually human-like face with AI enabled it to do human expression. It's scary as hell. I don't care. There was a human expression. I didn't know what that meant. And I'm assuming you wrote the patent already for this one. That's the same as personal IVR, just a really evolved version of it. So yeah. The loyalty concept, I think, is a bit of a tricky one, but to act on my behalf, certainly. How you guys feel about it?
Yeah, there's already a lot of them there, which acts in your behalf. Not truly intelligent ones, but if you think of a Roomba, for instance, that's a robot. That's on your behalf and it's yours.
All right, okay, that's a wrap.